This is the first unit for our course for database design. So this is the database design class for Oracle. And in this unit, I'm going to give you an introduction to database systems. So in this unit, we will talk about the difference between data and information. We'll talk about what a database is, the various types of databases, and why they're valuable assets for decision making. The importance of good database design, which we learned in this course. How many databases evolved from file systems, or modern databases rather, evolved from file systems, and some of the flaws in the file systems and why we evolved into using database management systems. So we'll end the lecture today talking about database management systems, which is the focus of this course, and designing the data structures that we're going to use in those database management systems. Let's begin our discussion talking about the difference between data and information. Data, and as you read in your textbook, you'll read about data, is raw facts. So raw facts are, when you think about raw facts, I think about something like a phone book, right? So a phone book is just a collection of raw data. There's really nothing useful in there. You have to kind of know what you're looking for to really effectively use a phone book. So nothing's really been processed yet. Here's another example, a 7-Eleven. When you go to the 7-Eleven and you buy something, a receipt is generated, and a collection of those receipts would be raw facts. But it's not information. You can go and look up an old receipt and you can see what somebody purchased last week or last month, but it doesn't give us really any real information about the business, just that collection of receipts. We have to process it and do something with it in order to do that. However, it represents the building blocks of information. And we do have to have a way to manage all of that raw data. We have to have a place to put it. We have to have a way to search it, a way to manage it, and so forth. So that's a lot of what our databases do. They do that data management. But information, we can extract information from our databases. So we can process that information. So for example, when I'm looking at my 7-Eleven example, if I wanted to know how many Slurpees we sold last month, I could do that from the raw data. We could process that raw data and get information. So that's how we get information from that raw data. It requires some context. It requires, and it gives us that bedrock of knowledge. And I'll give you an example of that. So take that 7-Eleven, for example. If you're a manager of a 7-Eleven, you may know that Slurpees generally sell better in the summer than they do in the wintertime. And you might know that because of your years of experience running a 7-Eleven. However, how would I know that if I didn't own a 7-Eleven or I didn't work there for years? How might I discern that information? Well, one thing I could do is take that raw data that I've collected over time, I could process that, and I could gain that knowledge from processing it. I could say, okay, on average, how many Slurpees did I sell per day in the month of July, and then compare that to the number of Slurpees sold in the month of January. And maybe I could even take that information, and when I learn something from that information, I can use it to make better decisions about the business. I know how much raw materials to order for my Slurpees. I know that when people buy Slurpees, they generally buy hot dogs, so I know that I have to buy more hot dogs and things like that. So we can get better knowledge. We can even use it to do things like specials. So I could, if I understand how many Slurpees I sell, maybe I'll calculate, okay, I don't sell as many hot dogs as I sell Slurpees. What if I could raise the number of hot dogs I sell by maybe offering them half off with Slurpees? And I could use that information, I could use that historical data as raw facts to try to do a scenario and determine whether or not I would make money if I did that, and try to estimate, how many more people would buy those products if I did that. So lots of good stuff you could do with that information, but we have to have a place to put those raw facts and that data and manage all that so that we can effectively extract that and use that information. So a database system, which we're going to learn about in this course, the primary goal is to have a place to store all of this data so that we can then extract it and turn it into information and use it in the business and use it more effectively. So a database is what allows us to do that. It's a shared integrated computer structure that stores a collection of end user data or raw facts of interest to the end user, like our receipts at the 7-Eleven. A database also has metadata. So the metadata is data about the data. In other words, it's data that describes the data. So the metadata basically describes the structure that we're going to use when we store our data. It tells us what type of data we're going to have. It tells us, where we're going to, how we're going to be able to connect data to other, to other information and things like that. So, and we'll learn a lot more about this as we go forward in the course. I don't want to confuse you too much yet, but the metadata basically describes the data. So when we talk about database schemas later on, we talk about tables and columns and rows. and attributes and things like that and data types. A lot of that stuff we'll find in the metadata, and that's a big part of what a database management system does. It gives us a mechanism to store the data about the data. So it describes data characteristics and relationships, and we call these systems generally database management systems, and I'll talk about that towards the end of this lecture. We'll talk more about database management systems, formally what they do, and how we define them. But from a very high level, they're basically a collection of programs that manages the database structure. And they manage access to that database. They manage how the information or how the data is stored on the file system and so forth. So it's a collection of programs that does all the minutia of managing the data on our drives and on our storage and how people access it and what we're allowed to store there and so forth and so on. So the role of a database management system is basically the intermediary between the user and the database. So it's a layer of abstraction between those raw facts, that data that we're storing, and the people that need to either store that information or retrieve that information. It enables data to be shared. It presents the end user with an integrated view of the data, sometimes enterprise-wide. We'll talk about those things later on in the course. It can receive and translate application requests into operations required to fulfill those requests. In other words, and it also hides the database internal complexity from application programs and users. In other words, the database abstracts all of the management of data. It handles that for us. So our applications, our users, all of these things that want to interact with that data, all does that through the database management system. So it's a layer of abstraction in front of our data. There's a lot of really good reasons to do this, and we're going to talk about that in this course. We're going to talk about all the reasons that it makes sense to do something like that. So some of the advantages of using a database management system is better integration and less data inconsistency. So data inconsistency is when we have different versions of the same data appearing in different places. And I'll talk about that when we look at file system, which are sort of an early primitive form of databases. It can increase end user productivity because they have faster, more efficient access to data in order to get that information and that knowledge that we talked about. We have improved data sharing, improved data security, data access, and decision making. These are all things that work much better with database management systems than if we didn't have a DBMS or that layer of abstraction. The data quality generally is a bit better. More accuracy, it's valid. The timeliness of the data, our ability to get access to that data, to get meaningful information from it. So there are lots of different types of databases. The simplest type of database is going to be a single user database, which supports only one user at a time. It usually would be on a desktop, maybe it runs on a PC. There's a bunch of little single user databases. Microsoft Access is probably a good example of a single user database, although Microsoft Access to some extent does support multiple users, but it is limited. And then you have multi-user databases, which supports multiple users at the same time. So these would be things like workgroup databases, which can support a small number of users, like Microsoft Access, newer versions of Microsoft Access. And then enterprise databases like Oracle, which we talk about in this class, or Microsoft SQL Server, or MySQL, or PostGre, and so forth. There's lots of different, Sybase, all these different enterprise databases. SAP, for example, which I'm sure many of you have heard of, a lot of these different companies. But those are all enterprise database companies. So centralized databases are those where the data is located at a single site, and when it's distributed, the database is distributed across different sites. And there's various reasons to do that. We'll talk about that, but distributed databases, one place we'll see those is in the cloud, which is created and maintained using cloud data services. So most of the databases that we talk about in this course are available in the cloud. For example, your book talks about Microsoft SQL Server, which you can use Microsoft Azure SQL, which is the same thing in the cloud. Oracle has some cloud offerings for their database engine, or third parties that you can use Oracle in the cloud, or have an instance of Oracle running in the cloud. For example, in this class, we're using Oracle in the cloud. When you set up your, when I set up your accounts with Oracle's Academy, you're actually using the internet to go out and access your databases and do all of your assignments. So you could use Oracle, for example, in the cloud. MySQL is the database engine behind Google and Azure's cloud offerings. So when you sign up for databases with those platforms, typically it's MySQL. So a lot of these are offered through the cloud as well. There's general purpose databases, which contain a wide variety of data used in multiple disciplines. Most of the database engines that we talk about in this course are general purpose. There's discipline-specific databases, which contains data focused on specific subject areas. For example, there are databases designed specifically for geographic information systems, or GIS. There are databases specifically for statistics and for science and for DNA and things like that, using things like the R language and so forth. So there are definitely some discipline-specific databases. Operational databases are designed to support a company's day-to-day operations. SAP, for example, is an example of an operational database, although any of them really could be an operational database. An analytical database stores historical data and metrics that are used for tactical or strategic decision making. So decision support systems are generally analytical databases. So you might hear the term data warehouse, where we store data in a format optimized for decision support. So we keep all of that historic data in a giant data warehouse so that we can use that data to make decisions later on, and we can turn that data into information. There's also, you'll hear the term online analytical processing, or OLAP, and basically the purpose for OLAP, and it works hand in hand with data warehousing, is it gives you the tools to process and model data from that data warehouse. So OLAP and data warehouses work very closely together. They work hand in hand. And then business intelligence, which captures and processes business data to generate information that supports decision making. And SAP, I use that term again. That's a company that has some platforms to do that, a database engine that can do that. Unstructured data is data in its original state, and structured data results from formatting or having some structure. Structure is applied based on the type of processing to be performed. We'll talk about, most of the databases that we talk about in this course are structured data. And you'll see how that works when we talk about data types and when you have to make decisions about data types and relationships and all of that design work that we do, we're usually doing because we're going to be working with structured data. It's a lot easier for applications and programs to share and integrate and so forth when you have structured data, because everybody can comply with that same data structure. Semi-structured data is sort of a hybrid between structured and unstructured. One good example of semi-structured is XML. You may have learned about XML in other courses. You may have used XML even outside your coursework. I'm sure everyone has probably had some exposure to XML, but that's a good example of unstructured and structured data, sort of a semi-structured. It has some structure to it, but that structure can be very easily adjusted. Anybody can make an XML to their own liking, to their own schema. And then there are ways to transform between different schemas. This is great for interoperability with APIs and things like that. And databases certainly support XML. There's, you'll see in Oracle some support for XML, some native support for XPath and things like that, which we'll talk about later on. But XML is a good example of semi-structured. And continuing with our theme here, database design focuses on the design of the database structure that will be used to store and manage user data. So in order for us to have that structured data for a very structured data type for databases, we have to have some design in order to do that. And we have to make sure we get that design right from the beginning. If we fail to get that design right from the beginning, it can be very difficult to make changes to that later on. So it takes a lot of thought, a lot of design, it takes a lot of engineering to make sure that we get it right. So that's what this class is about. We're going to focus heavily in this class on database design. We're going to look at data modeling, entity relationship modeling, some of these diagram techniques. We're going to talk about normalization. We're going to talk about data types and things like that. And we're going to talk about keys and how to identify records, foreign key constraints, all of these things that we need in structured databases. So a well-designed database facilitates data management. It generates accurate and valuable information. But a poorly designed database causes difficult to trace errors and can make it difficult to work with. So let's take a step back in time when databases really didn't have much structure. We'll talk about the old days when we used file systems as databases. So a long time ago, let's go back to before we even had computers. Go back to 1946. You walked into any business in America, most businesses in America, or really anywhere in the world, you would have a manual file system. Right? So I'm sure we've all seen, probably old movies where they have files everywhere, and you had armies of secretaries that managed those files, and they were like our database management systems, a very primitive database management system. One thing that you probably know about those old systems, those old filing systems, number one, it's very difficult and time-consuming to aggregate data from those old file systems. If you wanted all of the information about the Jones account, you would tell a bunch of secretaries, go find me all the Jones files, and they'd have to go combing through all the files and gather everything up and then bring it back. And that could take days for you to get that information if you have a rather large business. And that's just in your office. What if you need the stuff on the Jones account from some other office? You'd have to call them, they'd have to gather the information, and they'd have to coordinate with other offices. So you could see how that would take quite a bit of time, and it's not very efficient. So going forward, then we came up with computerized file systems. So you had these data processing departments in companies. They got these big mainframe computers, and they would store all of their files in computer file systems, so in computer files. And the thing about computers is that they're very fast at searching. They're good at pattern recognition. They can find things and aggregate things very quickly, and it makes it much easier to share information on a computer. So some of the problems with the manual file systems went away. However, there were still some issues which we're going to talk about. And then from the computerized file systems, kind of the next evolution was to things like spreadsheet programs like Microsoft Excel. Then you started to see programs like Excel and Access popping up and getting used in offices as well. But alongside of that, database management systems were also evolving around that time as well, which is the focus of this course, these database management systems. And to some extent, that the bottom part of this slide that you see here, the file system redo, that's still happening today. We still have people using Microsoft Excel. We still have people using Microsoft Access. And Excel is a great tool. There's a lot of really interesting things you could do with Microsoft Excel. But it doesn't take the place of a database management system. And likewise, a database management system doesn't really do what Microsoft Excel does. There is some data analytics and analysis that you can do in Excel that you really can't do in a database unless you write an application or a program to do that. So they can work hand in hand. In fact, you can integrate Microsoft Excel with database management systems so they can get their data from a DBMS in order to work with that data to do analysis and to get analytics and basically to get information like we talked about before. So some of the terminology for basic file systems, you had data, which is the raw facts, like a telephone number and a telephone book, customer information, which would be just data files. Fields were a character or group of characters that had specific meaning. A record would be a logically connected set of fields. So for example, some fields about customers could be their name, their address, their phone number, their ID number, and so forth. And a collection of those fields that describes one customer would be a record. And then a file is a collection of related records. For example, I might have a file for customer Jones, and it contains all of their orders and all of their payments and all of those sorts of things. So it might look something like this. You would have a computer system, it would have a customer file, it would have a sales file, and it would be sharing all these files, but it would be a flat file system in the sense that there is no DBMS managing any of this stuff. We're going to talk about that in a little bit. So you would have to write programs that would basically be able to process, create, and work with those files in the file system directly. So you would write a program that would use that file system. And one of the challenges with these old file system type programs, they worked very well. I don't want to say that these were not good programs. A lot of these programs worked great. The problem was, let's say you owned a business and you paid a programmer or you bought some software to run your business, and it stored things in these flat files, and it had a certain way that it stored information, and the programmer just developed their own formatting and so forth for these files. Well, let's say you decided to switch to another vendor, or let's say that programmer went away. Maybe he got hit by a bus. Who knows? You don't have access to them anymore. All of your data is locked up in this file format that you really have no understanding of. So in order to use that data, you now have to hire a different programmer, has to analyze that file, try to reverse engineer it to figure out how it worked. And while that sounds relatively easy, some of these file systems, these programs that used file systems, they were pretty complicated. Some of them stored the data in base 64. Some of them used binary. They had their own formatting and delineation in the files and so forth. So lots of things that could be very different between different systems. So it could be rather confusing. So it's not as simple as most people thought. So again, you lock up your data in this proprietary format. It makes it difficult to have interoperability. So lots of bad things. So here are some of the problems. Lengthy development times. It took a long time to develop business systems, because not only did you have to develop the business logic and the business systems, but you also had to develop those data structures and the database mechanisms of persistent storage on the back end. So all of that stuff you had to do, and it takes a long time to develop a very efficient file system for storing all this data and working with this data. It's a significant amount of engineering that you have to devote to that. Difficulty of getting quick answers because they're not always very fast. A complex system administration because they're all different. Lack of security and limiting data sharing. Sometimes they didn't even have those types of features. And it took a lot of programming to work with and to develop those systems. So some of the other problems: structural dependence. Access to a file is dependent on its own structure, which I just talked about. In other words, all the file system programs are modified to conform to a new file structure. In other words, if you made any change to the file structure, you had to also change all the programs that access those files. Even if you had multiple programs using the same files because they're doing different things, they would all have to be aware of any structural changes. So they were all dependent on that structure of those data files. Whereas structural independence, which is our goal with database management systems, is where the file structure is changed without affecting any of the application's ability to access the data. So we can make changes to the data structure, and we can either abstract those changes to different applications, or it's very easy for those applications to adapt to those new file structures. Data dependence is a problem. It's where data access changes when the data storage characteristics change. Where data independence is data storage characteristics are changed without affecting the program's ability to access the data. So if something about the data is changed, with data dependence, if you make a change, with something about that data, it makes it very difficult for those systems to access it without making changes. Whereas with data independence, you don't have to make those changes in the application programming. So the practical significance of data dependence is difference between logical and physical format. Which we'll talk about logical and physical databases here in a little bit. One of the other problems is unnecessarily storing the same data in different places, and you ended up with these islands of information, or what I like to call silos. You would have siloed data, scattered data locations. I'll give you an example. Take the college, for example. Let's say they were using an old file system type database, and maybe they have a system that can manage student information, that can keep track of all the students' information, keep track of which classes you're enrolled in, and keep track of your grades. That would be sort of a typical registration system for a college. But then let's say the college decides to start a financial aid department, and that financial aid department really can't have access to the student records, and they develop their own program to manage financial aid. But that program needs to have information about students. So they get that information from students from the other system somehow, and they load it into their own system. And then they maintain their own database. So if a new student is registered, the information goes down to the financial aid department, and they also put that student's information on their side. But let's say that student changes their address or their phone number or something like that. That information might get updated in the registration system, but it might not get updated in the financial aid system. Now, from a student's perspective, they told the college, right? To you, a student, the college is any employee of the college. You don't really make the delineation between financial aid or registration or counseling and so forth. These are all just the college. And you make the assumption that if I give my phone number to one department, that they're going to share it with whoever needs to get it in the other departments. And of course, we all know that that's not really the case. So having these islands of information increases the probability of having different versions of the same data. So we'll have, over time, different versions of that same student's address, for example, in different departments, which is bad. We want to try to avoid that, and hopefully a DBMS can help us do that. Poor data security. We have data inconsistency, increased likelihood of data entry errors when complex entries are made in different files, right? So if you have this file system, well, I'll talk about each one of these. A lot of these older file systems didn't really have security mechanisms that could integrate outside of their own programs. So while there might be some security mechanism baked into that program, that doesn't stop somebody from just reading data directly out of the file, for example. Data inconsistency we talked about already. Increased likelihood of data entry errors. So if you have the complex data that has to be entered multiple times in different places, that's another opportunity for error. And that's really what normalization helps us do. We'll talk about normalization later on in this course. And a data anomaly develops when not all of the required changes in the redundant data are made successfully. So, and a good example of that is the what I just talked about when we update, say, a student's phone number in one place, but it doesn't get updated in other places. That would be a data anomaly. So in your textbook, they talk about update anomalies, insertion anomalies, and deletion anomalies. We're going to talk about this in much more detail in Unit 5 when we discuss normalization. But these are all errors that can happen when we don't have a structured data format. And again, one of the things I want to make clear here is that all of these things are possible, right? So all the downsides I'm talking about with these old file management systems, file-based database systems from the old days, they could certainly support all these features I'm talking about. They could certainly, have all this stuff, but it takes a lot of engineering and it takes a lot of software development and a lot of planning and all of this other stuff to make a good system that has all of these attributes. So a DBMS does that for us. And that's really the purpose of a DBMS, is that it takes all of these things that we need and that we want in data management, and it gives us a system that does it for us without our application programmers having to worry about that. So with DBMSs, we basically are taking the data and we're moving that to a layer outside of our application, outside our application's control. So now my application simply needs to tell a DBMS I want to store some information or I want to get some information, and that's it. We don't have to worry about all of this other stuff that I talked about. We don't have to worry about maintaining consistency and data types and all these other things that our DBMS does for us. We don't have to worry about security. That's all handled by the DBMS. So lots of good reasons to use the DBMS. In the current generation of DBMS software, it stores data structures, relationships between structures, and access paths. And we'll talk about that in more detail later on. It defines, stores, and manages all paths and components. So everything is basically managed by that DBMS. So basically everyone accesses the DBMS, whether it's applications or people, and it abstracts the access to the actual data that's stored in some data structure on a hard drive somewhere, or in memory for that matter. All right, this is just another image from your textbook. This is you can find this in the textbook, but basically it's showing you the relationship between the DBMS and all these different components that work with the DBMS. So with a DBMS, you have a data dictionary. The data dictionary is basically where we store all of the data elements and their relationships. I know I'm using some terms here that maybe you're not familiar with yet, but we're going to talk about data dictionaries. We're going to talk about relationships later on. But just understand for right now that this is something that we have to keep track of in a DBMS in order to meet all of those goals that I talked about earlier. We have data storage management, for example, performance tuning to make sure we can access our data in a timely fashion and we can work with that data. Data transformation and presentation, which can make sure that different systems can use that data. Security management, which enforces the user security and data privacy and so forth. Again, our DBMS has all these mechanisms baked in to give us security. It has multi-user access control, so different, hundreds, even thousands of people can access databases at the same time, and we don't lose our data integrity because it has mechanisms built in to make sure of all of that stuff. And we're going to talk about that later on in this course. We'll talk about that after the midterm in the second half of the course. Backup and recovery management, again, we'll talk about that in the second half of the course. Data integrity management, minimizing redundancy and maximizing consistency, that we actually talk about in units 4 and 5 before our midterm. Database access languages and application programming interfaces. So basically a database management system gives us a common language that applications can use to interact with the database engine. What we're going to learn about in this class, and some of you may have learned about this already in our CISM 167, is SQL, or the structured query language. So SQL is the de facto standard language we use to interact with the database. Here's the beauty of SQL. Oracle uses SQL, Microsoft uses SQL, Azure uses SQL, MySQL, Postgre, all these different database engines, they all use SQL. So if I write an application, or if I'm an application developer, if I know SQL, then I know the language to work with just about any major database engine out there in the market. So, and to take it one step further, I can write an application that could be database agnostic. In other words, You don't have to use Oracle or MySQL or Microsoft with my application. I can write my application in a way that it can work with any of those database management systems. So it really kind of separates that data management layer from the application and business process layer. So it gives us a lot more efficiency in application development and so forth. It also has communication interfaces, so we can work with the database over the network, named pipes and so forth and so on. We'll see that with Oracle as well. Some of the disadvantages of I'm talking about all this great stuff about DBMSs. There are a few disadvantages. One thing is they're expensive. A good DBMS, Oracle, for example, is not known for being an inexpensive product. It's extremely expensive. To buy an enterprise Oracle platform for a business could be, in the hundreds of thousands of dollars to buy that. It's certainly out of range for most of us to put one in our home. Although Oracle does have versions that you can use. In fact, they have one version that's free, which is Apex, which is what we're using in this course. But you could actually install that on your own computer if you wanted to. But there's a wide range there, and it certainly can cost a lot. Also, you have to have DBAs to manage those systems because the management is very complex on DBMSs because of all these different features that I talked about. So you have to have a staff that can manage it. You have people that are trained to manage it, and we'll talk more about that in just a few minutes. Maintaining currency. In other words, you have to keep them updated. You have to be on the latest versions. You have vendor dependence. Some vendors require Oracle. Some require Microsoft. Again, they don't have to, but some vendors write their applications in such a way that you have to use those DBMSs, and then you're kind of locked into one vendor. And what happens in a lot of businesses, we have one major vendor that requires Oracle and another major vendor that requires Microsoft. So we have to have two different database engines. And now we're back to having our siloed data again because now they both have to have their own version of the same data. There's ways to mitigate that. We'll talk about that later in the course. Frequent upgrade and replacement cycles. Microsoft comes out with a new version of their database engine probably every 2 years. I think we're up to Microsoft SQL Server 2016 right now. Oracle comes out with a new version on roughly the same frequency. Does that mean you have to upgrade them? No, you don't have to necessarily upgrade them. But generally, some vendors will ask that you do that. Some require that you do that for a variety of reasons. Sometimes they add additional functions, and we'll talk about functions later on. But sometimes they add new functionality that supports new things that might be available in the standard that other vendors have added that that they need. So we'll talk about that stuff later on. So there are certainly some disadvantages, but it's strongly, I think almost anyone will tell you that most of the industry strongly favors DBMSs over file management systems, for sure. So even though there's a few disadvantages here, but when I talked about management complexity, I talked about some of the, having to have skilled labor in order to work with these systems. So these are all the different types of careers, and this is from your textbook. So there's lots of different types of careers that you could explore. So for example, database developers, which create and maintain database-based applications. You have database designers, which design and maintain databases. You have DBAs, which administer those databases. Analysts, architects, consultants, a database security person, which is responsible for data security, which is becoming more important today because we put a lot of sensitive information in these databases. Cloud computing data architect. Now we even have people that are specialized to work with databases in the cloud. So lots of different specialties in the database world. It's certainly a lucrative business, and that's why most of you, I think, are taking this class so that you can expand your careers into the database realm. And I certainly recommend taking this class. There's also another class at this college. Lots of classes that you can take, and certainly other places you can learn about all this stuff. But it's definitely a growing field for sure. I think the Department of Labor indicated that database DBAs or database administrators are one of the faster growing career fields right now, along with many other computer type fields. One thing I do want to mention here too is the database analyst. Analysts are there's analysts in just about all areas of IT, and one thing I do want to mention about that is that generally, no matter what area you're pursuing in IT, you're probably going to be looking at multiple different skill sets, not just databases. So even people that are in college for programming, that are taking all of our programming classes like C++ and Java and things like that, they would also expect it to be aware of databases, just like it would be good if you're focused on databases to understand application development and so forth, because they really work together a lot. Also, systems integration and systems development and things like that, which you might learn about in the systems analysis and design course. All of these things are all kind of intertwined. So that's what we're going to be talking about throughout the rest of the semester. Just wanted to give you a nice, a quick overview of all of these topics. And in the next unit, we're going to start talking about database design. So we're going to talk about some of the techniques we use in database design and some of the vernacular, and then we'll get into some modeling, and then we'll start talking about some SQL, and that'll take us to the midterm for the first half of the course. If you have any questions, please let me know. Thank you.